All right, topic 5.3, quick review. Remember, this is the equation for the internal resistance of a battery. In truth, batteries are not perfect. They dissipate some energy rather than supplying that to the cell. So to find what that internal resistance is, you use the equation epsilon, where epsilon is the unloaded voltage of the battery. This is the voltage that the battery has when there is no external resistor or no external load connected to it. This should be equal to I, the current through the circuit, that the current passes through the battery, it passes through the resistors, the wires, everything, times quantity capital R, where R is the resistance of the external resistor or the external load, plus lowercase r, where lowercase r is the internal resistance of the battery. It's lowercase because the internal resistance is usually much slower than the external load. IB expects you to be able to determine the internal resistance of a battery, which you would do by analyzing this equation first. I times R, I times capital R, this, I'm going to distribute this I to everything. This changes the equation. Epsilon is equal to voltage, where the voltage is the voltage drop across your external resistor plus the current in the circuit times lowercase r. Now you cannot analyze lowercase r in a real battery, but you can measure voltage and you can measure current. So the way to determine the internal resistance of a battery is you plot the voltage across like a variable resistor. That's a resistor of resistance that you can change versus the current that you measure in the circuit using the ammeter. When you plot V versus I, the voltage acts like your Y values and the current serves as your X values. And so if I want to analyze this equation as a Y equals mx plus B in the Y equals mx plus B form, I rewrite this equation. My voltages are the Y values, and I'm just manipulating this equation up here to write it in terms of Y equals mx plus B minus R times I are my X values, plus epsilon. This means is that my slope value is the M. The slope value should be negative R. These are my B values. This would be the epsilon, or I'm sorry, the y-intercepts would be epsilon. So you would end up generating a plot of that looks like this. You have a negative slope, a straight line. It's a linear function, negative slope. The y-intercept is the unloaded voltage of the battery epsilon, and the slope value is equal to negative internal resistance. Okay. Question number 1, you should be able to solve this. This is actually from topic 5.2, but you will use this equation, power equals V squared over R. You'll do this twice. Just read, compare what is changing in the equation and determine what the correct answer is for P. Question number 2, this is from topic 5.3, so use this. Epsilon is equal to I times R plus little r. Should be able to solve for current in this case, and once you solve for current, you can determine which of these answers is correct. Make sure to check the power dissipated in the battery. The power dissipated in the battery because of its internal resistance would be I squared times its little r. So this is for the dissipated in the battery. Okay, so you should be able to check those. Number 3, a circuit is formed by connecting a resistor between the terminals of a battery of electromotive force EMF 6 volts. The battery has internal resistance. Which statement is correct when 1 coulomb of charge flows around the complete circuit? Remember, 1 volt is equal to 1 joule per coulomb, energy per unit charge. If you have internal resistance in this circuit, if the battery has internal resistance, that means that not all of the potential is dropped across the resistor. Some of the potential is dropped across the internal resistance of the battery, so you get rid of choice A. Choice B, 6 joules of thermal energy is dissipated in the battery. What this means is that this is a totally inefficient circuit. None of the current is actually flowing. Rather, all of the energy is lost as heat dissipated in the internal resistance. So no, that would mean no current is actually flowing. 6 joules of chemical energy, or this would mean a short. The battery shorting. Okay, choice C, 6 joules of chemical energy is transformed in the battery. A battery is a device, or is a device that transforms chemical energy into electrical energy. So yeah, I could say this is true. Choice D, 6 joules of thermal energy is dissipated in the resistor. What that means is that all of the electrical energy that's going into the resistor is just being lost in the form of heat. No, it'd be choice C here. This question, you should be able to answer this as 5.2, but if not, build this in PhET and check it. Remember, power is proportional to current. So, well, power is proportional to current squared. Okay, question 5. This is internal resistance, so you will use this equation. Epsilon is equal to I times big R plus little r. Get your current. And then the voltage dropped across this external resistor equals I times R. Let's see. Oh, right. Epsilon is equal to I. So this equation, this becomes V plus I times R. You should be able to get the voltage from the given stuff. The ideal voltmeter reads 3.2. Okay, you should be able to get current then. This is your voltage, this is little r, this is epsilon. Get the current, and then once you have the current, once you have I, you have your voltage. Voltage is equal to I times R, and then you can solve for R. Okay. What are the characteristics of a primary cell? The primary cell converts chemical energy to electrical energy, and primary cells, they're like your alkaline batteries, they're not rechargeable. So 6 is choice B. 7, this is topic 5.2, resistivity. If you half the diameter, so just remember wires have a cross-sectional area that's equal to the area of a circle. So the cross-sectional area is pi r squared. Pi is a constant, it doesn't change. If you're changing the diameter, you're changing the radius. And you'll use the equation resistivity. Resistivity is the rho is equal to R. In this case, the R is constant, same resistance, times a new cross-sectional area over length, and length is also a constant. So see what happens to resistivity when you change area. We have a cell with an EMF 2 volts, negligible internal resistance, is connected across a 1 meter long length of uniform resistance wire XY. The free end of the flying lead of the voltmeter can be connected to any position on the wire. So this is easy. Resistance is proportional to length, and I know that the voltage across a resistor is also proportional to resistance. And so the length of this resistor should be proportional to the voltage across it. So if you have the full length of wire, all of the 2.0 volts supplied by the battery gets dropped across the 1 meter length. But if you're now only a quarter of the length down, you should only drop 1/4 of the voltage supplied. Question 9, internal resistance. So this again, you're using the equation from topic 5.3. Same for question 10. Question 11. The diagram shows a potential divider circuit used to measure the EMF E of cell X. Both cells have negligible internal resistance. State what is meant by the EMF of a cell. The EMF is the work done per unit charge in driving charged particles in a complete circuit. So that's the EMF of the cell, the electromotive force. It's not actually a force, It's just what Faraday thought was a force, but it is the work done per unit charge or per coulomb in moving or driving charged particles in a complete circuit. All right. AB is a wire of uniform cross-section and length 1.0 meters. The resistance of wire AB is 80 ohms. When the length of AC is 0.35 meters, the current in cell X is 0. Show that the resistance of the wire AC is 28 ohms. So the full length A to B is 1 meter, and this has a resistance of 80 ohms. A to C is 0.35 meters. What is its resistance? This is just proportionality. Resistance is proportional to length. So with 1 meter long, it's equal to 80 ohms. But if the length is down to 0.35 meters, what is X? Solve for X, and it should be equal to 28 ohms. Okay, determine E, where E is the EMF of the cell. Okay, so right now we have resistance AC here. We can use Kirchhoff's loop rule, which states that the sum of the voltage gains and the voltage drops in any loop that you draw around your circuit should be equal to 0. This is just conservation of energy. So I'm going to calculate the voltage dropped across A to C. We have another battery in the circuit, and this battery is driving current around at least this part of the circuit. Okay, and so current flows through the entire length of the resistor, but in terms of this right side of the circuit, this right side of the circuit is only connected to AC. So what we can do is get the voltage across AC, and that should equal the voltage of the cell. So the voltage, right now there's no current flowing in cell X. Okay, yeah. So what that means is that the voltage dropped across here, the voltage drop, which were negative, plus the voltage gains equals 0. Voltage gain, the gains are given by the battery, equals the voltage drop. So the voltage drop in the right-hand loop is just from A to C. So the voltage of cell X should be equal to I times the resistance of A to C. Okay, so calculate this. And then we determine E. Yes, this current in cell X is 0. Okay. Cell X is replaced by a second cell of identical EMF, but now it has internal resistance 2 ohms. Comment on the length of AC for which the current in the second cell is 0. All right, so now if this cell has internal resistance, it has even less energy available to drive current, and it wasn't driving current before because it didn't have enough energy. With internal resistance, with length AC, it's still not going to allow current to flow, not enough energy. In fact, you could possibly even make it shorter, length AC, and it wouldn't be able to drive current. So you could state that at this length, with internal resistance, current still does not flow. Thanks for watching, guys, and study well.